Hello and welcome to this video on the backpropagation algorithm. So this is the third video in our fourth unit on neural networks, and this is hopefully going to clarify a lot of the training process and some of the words that we've kind of been just throwing around in these other videos, like gradient descent. What does that actually mean and how is it used to train neural networks? So some of those concepts may have been kind of confusing up to this point. Hopefully we can dive into that now and clear up some of those discrepancies. So this is a presentation by Onyx. Thank you for listening, and hopefully this will expand your understanding of training neural networks. So to start, let's talk about a simple case, and that is training a single perceptron. For this process, we can use online learning, and in online learning we do not write the error function over the whole sample, but on each individual instance. So starting from an initial random weights, at each iteration we would adjust the parameters a little bit to minimize the error without forgetting what we have previously learned. So if this error function is differentiable, which we will see it is later, we can use the process of gradient descent to accomplish this goal. So this approach saves us the cost of storing the training sample in an external memory and storing the intermediate results during optimization. So computationally efficient, and the problem may be changing in time. So another advantage of this is that if the sample distribution changes, which it will when we introduce new instances, the training set cannot be chosen a priori. So for example, we may be implementing a speech recognition system that adapts itself to its user. So it can handle a changing sample distribution. And finally, there may be physical changes in the system. For example, in a robotic system, the components of the system may wear out or sensors may degrade. Training with online learning is going to handle all of those problems. So let's look at the form of a gradient descent function. So first, if the actual output is equal to the desired output, no update is done. When it is done, the magnitude of the updates increases as the difference between the desired output and the actual output. So that is why we have the subtraction in the middle here. And then when an update is done, its magnitude depends also on the input. So a larger input is going to have a larger effect. If the input is close to 0, its effect on the actual output is small, and therefore its weight is also updated by a small amount. In general, the greater an input, the greater the update of its weight. We also have the learning factor, and the magnitude of the update depends on the learning factor. If it is too large, updates depend too much on recent instances. It is as if the system has a very short memory. If the factor is small, many updates may be needed for convergence. So the learning factor is going to affect how quickly our network is updating itself and how gradual it is applying these changes to the parameters or weights. So this is the general form of a gradient descent error function, and this is how we update the weights of a simple perceptron. So when we have multiple layers, this gets a lot more complicated. Networks with hidden layers between the input and output are able to form classification with nonlinear discriminants and regression with nonlinear function. How is that if we're simply doing linear updates to our parameters? Well, hidden layers apply a nonlinear activation function. So in this diagram in the left, we have a two-layer system. We have our inputs down at the bottom X, and in the middle we have our first layer, which is going to apply a sigmoidal activation function, and then we have our outputs Y. And each step has different weight vectors applied to it. In regression, there is no nonlinearity in the output layer when calculating Y. So classification would use a nonlinear threshold function, such as the sigmoid. So each neuron applies the nonlinear sigmoid function to its weighted sum, and it does that in the first layer. In the second layer, we are just going to take the hidden units as inputs and train these in the same way that we would if we only had one layer or a single perceptron. So if the hidden units outputs were linear, the hidden layer would be of no use. A linear combination of linear combinations is another linear combination. So this is why the sigmoid is used, and the sigmoid is continuous, a differentiable version of thresholding. We need differentiability because the learning equations we will see are gradient based. Another sigmoid nonlinear basis function that can be used is the hyperbolic tangent function, which would range from -1 to +1 instead of 0 to +1. In practice, there is going to be no difference between using the sigmoid and the hyperbolic tangent. However, it's important to mention because it comes up as in both ways. So when we move on to training one of these networks with multiple layers, this is when we're going to actually introduce the concept of backpropagation. So training multiple layers is the same as training individual perceptron, except the output is now a nonlinear function due to the nonlinear basis functions in the hidden units. So the hidden units are the important part. And the output is a nonlinear combination of the nonlinear basis function values computed by the hidden units. It can be said that the hidden units make a nonlinear transformation from the d-dimensional input space to the h-dimensional space spanned by the hidden units. And in this space, the second output layer implements a linear function. So if we once again look at our diagram of this two-model system, and we consider the hidden units, the hidden units are going to be inputs, and the second layer is a simple perceptron. As such, its parameters are updated normally, but for the first layer weights, we need to use the chain rule to calculate the gradient. So it's actually in this first layer that we get backpropagation. And this is the chain rule for that error function, and it is used to update these weights. So it is as if the error propagates from the output y back to the inputs, and hence the name backpropagation. So here, we don't actually know what the output of the hidden units should look like, so it's hard to just update them. We can't compare them using a least squares type function of the form we looked at for the single perceptron. We have to use the chain rule because, once again, we don't know what their output should look like. However, we still need to update the weights, and we can do that using this function. So let's take a look at an actual example of a nonlinear regression problem, and hopefully this will be clarified. So here's a nonlinear regression example. Once again, we have our same two-layered model, just like we did in the other slides. So a single output is calculated as just like we have seen before. We have the summation of our weights times the output of our hidden layer plus our bias unit. Actually, in this additional layers, we are going to include an additional bias unit for each layer that we have. The error function for all of these is just our expected output R subtracted by our actual output Y. And we're going to square that and take a half of this summation. So the second layer weights are a lot more complicated, and they can be, well, actually this is the second layer in the output Y uses the same gradient. This is the actual gradient descent, and you have here the R, the form of the output, or the output value that you're expecting, minus Y, what we actually got, times our inputs Z, and we have our learning factor in the front here as well. So this is the gradient. But for the first layer weights, much more complicated, but they can be found using the differential equation or the partial differentials that we had in the previous slide, and this is what that looked like. I'm not going to dive into this math, and you can follow along with each step if you so desire, but ultimately what it produces is a way to update the weights in the first layer based on the output of our second layer. So we don't know what the output of our hidden unit should be, but we can update the weights by backpropagating from our output using gradient descent and partial derivatives. So this is very valuable. We can optimize our weights for multiple layers, and this unlocks the power of neural networks and unlocks nonlinear neural networks. Individually, perceptrons are not that powerful. We have plenty of linear classifiers and linear regression examples. However, we can achieve nonlinearity by applying hidden layers that have a sigmoidal activation function, and they can be trained using backpropagation. So backpropagation was a mathematical advance that really unlocked the power of neural networks. Once again, the perceptron was theorized long before it was commercially used, simply because it couldn't be trained. But using this process, we know how to update the weights, and we know how to update them properly. So this unlocks the power of neural networks, and it's really important to understand how this works, and at least that is possible for this to work. So there are some different implementations of backpropagation. We talked about online learning, where we update the weights after each instance. However, with the learning equations given, for each instance, we're going to compute the direction in which each parameter needs to be changed and the magnitude of this change. So online learning, we're going to do that after each instance. However, in batch learning, we're actually going to accumulate those changes, and then we're going to make the change in one step after a complete pass over the whole training set is made. And this complete pass is called an epoch. So in this method, we have to use smaller learning factors because we don't want to make huge steps and then accumulate all those changes, because that could get inaccurate and slow down convergence. We want to use a smaller learning factor so that when we accumulate all those changes, it is still moving in the right direction. But we'll talk about that more in our next video when we talk about training procedures. How do we use epochs and batch learning to ensure convergence? So keep listening. We'll talk about how this is actually used to train networks in the sense of choosing parameters, or choosing maybe online learning versus batch learning, choosing an activation function. Is there really a difference between the hyperbolic tangent and the sigmoid? We'll look at that a little bit more in our next video. So thanks for listening to this presentation. I hope you got a lot out of it. Thank you very much.